Okay, good day. This is Tuesday. This is the video for Tuesday, December the 2nd. We are going to talk about diffusion and molar volume. That's 5.10 in your notes. And of course, the first thing we need to look at is the definition of diffusion. That word diffusion, it just means a scattering of gas molecules going from high concentration to low concentration. So if I have 2 beakers of gas and I have a whole lot of gas particles in one and only a few gas particles in another, then they will always flow from the high to the low. That's diffusion. If there was some way that these two were connected, if there was an opening, let's do it this way. Let's say these are closed containers and they have an opening. Okay, then they will always flow from the high to the low, always. They will not go back the other way. They will always flow from high concentration to low concentration. Okay, and the rate of diffusion, or how fast they do this, depends on the size of the molecules, or the velocity of the molecules. Rate of diffusion depends on the velocity of the molecules, how fast they're moving. At the same temperature, small molecules, a smaller mass molecule will diffuse faster than a larger mass molecule. And that ought to make sense. The heavier it is, the slower it's going to move. There's also something known as effusion. And effusion is the movement of gas through a small opening. Gas molecules also have the ability to pass through a tiny hole or a tiny opening. And of course, the smaller mass molecules will do this faster than the larger mass molecules. An example of this would be like a hole in a balloon. Okay. If I have a balloon and I've punched a tiny little hole in it and it's tied off there, and I punch a tiny little hole right here, well, automatically, without being able to stop it, all the gas molecules are going to effuse out that tiny opening, and that's known as effusion. Okay? We've talked a little bit about moles before. Moles is just a unit. It's a standard unit for a large number of things, and 1 mole of something is always equal to the atomic mass of that thing. So 1 mole of particles, whether they're ions, atoms, molecules, has a mass in grams that's equal to 1 atomic mass unit. So for example, if a mole of any type of particle has a mass of 4.02 grams, then a single particle has a mass of 4.02 atomic mass units. Let's look at a better example. Let's look at this one. A single atom of hydrogen has a mass of 1.0079 atomic mass units. This is its atomic mass from the periodic table. So 1 mole of hydrogen would equal that many grams. If we had carbon, for example, carbon's mass on the periodic table is 12.00 grams. So 1 mole of carbon would equal 12.00 grams. The atomic mass units there and the grams are kind of interchangeable. Atomic mass unit is a relative unit, so we can switch that and grams back out. Okay, next page. Molar volume. Before we do molar volume, let's do one example of a mole in terms of a compound. Let's look at carbon dioxide. To find out how much 1 mole of carbon dioxide weighs, what I'm going to do is I'm going to add up the atomic mass of every element in carbon dioxide, which means I have 1 carbon, so that would be 12.00 grams. I have 2 oxygens, which would be 2 times 16. And then if I add those up together, that's 12 plus 32, which gives me 44 grams in 1 mole of CO2. So to find out how many grams are in a mole of a compound, you're simply going to add up the atomic mass of every element in that compound. All right, with that said, let's look at molar volume. If I have two different gases at exactly the same temperature and pressure, then they will have the same volume. At a given temperature, the kinetic energy will be the same, no matter what their size or mass is. If you're at a certain temperature, they're going to have the same kinetic energy. Greater mass is going to travel slower, lighter mass molecules are going to travel faster, but the average is going to be the same. At the same pressure, there was an equal number of molecules in the two containers. So, knowing that at a given temperature, they're all going to have the same kinetic energy, at a given pressure, then you're going to have an equal number of molecules in those two containers. We can then say that at equal temperatures and pressures, equal volumes of gas are contained in the same number of molecules. And this is what's called Avogadro's law. We let N stand for moles, V stand for volume, so we can restate our law. Let's see. That's not the law yet, so hang on to that. So the law is, it can be concluded that 1 mole of any gas at standard temperature and pressure, that is a set pressure and a set temperature, will occupy the same volume as 1 mole of any other gas at standard temperature and pressure. So volume occupied by 1 mole is always going to be equal to the same volume. And they have that listed as 22.4 decimeters cubed. An easier and more common thing to say is 22.4 liters. So Avogadro's law helps us to come to the conclusion that 1 mole, or the molar volume of a gas at standard temperature and pressure, is equal to 22.4 liters. 1 mole is equal to 22.4 liters. That's the molar volume, and it only happens at standard temperature and pressure. Okay, and that's what Avogadro's law states, that at the same equal temperatures, equal pressures, then you will have equal volumes of gas and you will have the same number of molecules in those two volumes of gas, no matter what those two gases are. 1 mole of a gas at standard temperature and pressure is 22.4 liters, regardless of its identity. Doesn't matter what gas it is. If you have standard temperature and pressure, 1 mole of that gas is always 22.4 liters. Okay, and that's it for Unit 5. So we have completed this unit, and we have 4 laws that you need to make sure you know. They're Boyle's, Charles, Gay-Lussac, and combine. Make sure you know those formulas before we have the test on Friday, and make sure you know how to work those types of problems with those gas laws. All right, have a great day.